Alright, now I want to go through the same example that we did in class. That was a neutron which breaks apart into a proton, an electron, and an antineutrino. So we figured out why by using the elementary charge, baryon charge, and lepton charges. But I want to add the energy. So in the book, when they wrote out that example, they did the charges to make sure that they were balanced. And then they also looked at the energy. Now the rule for nuclear reactions is the following. Oops. The reactions always go from high nuclear energy to low nuclear energy. Okay. So we've also said that, for example, other carriers, like when we talked about heat, we said that entropy goes from high temperature to low temperature, and when we did rotation, we said that angular momentum goes from high rotation speed to low rotation speed. Now, for nuclear reactions, the reactions go from high nuclear energy to low nuclear energy. So let's take an example. Let's see if this one right here is really an example. So in order for this reaction to go, we'd like to know whether a neutron, we'd like to see if this is really a higher nuclear energy than that. And here's the way we do it. We write down the rest energy for all these particles. So what is the rest energy of the neutron? Rest energy of the neutron is 150 .525 picojoules. I'm not going to write that down everywhere, but all these numbers will be in picojoules. So this is before. After after the reaction, the proton has a rest energy of 150.320 picojoules. The electron has a rest energy, and again, the electron rest energy we get by multiplying the electron mass, which is written in your textbook. So that would be electron mass times c squared. So if we apply that equation, use the electron's mass, multiply it by c squared, we can find out what the rest energy of the electron is. We could also say the rest energy is just the mass in units of energy. Same thing. So this is the proton. The electron has a rest energy of 0.082 picojoules. So the neutrino has a rest energy of 0. Now it turns out the neutrino's rest energy is not precisely 0, but actually it's incredibly small, way smaller than an electron, and it's so small that we don't actually know what it is. But for our calculations, we're going to use 0 for the neutrino rest energy. So that'll be 0. So if we add all these numbers up, then we get a total energy on this side of the equation of 150.402 picojoules. And over here we have 150.5 5, 2, 5. Okay, you notice that this total energy is greater than that total energy. There's no separation energy in this situation because we don't have real nuclei. We just have a separate neutron by itself and a proton by itself and an electron by itself. So nothing is bound together in a nucleus, so there's no separation energies for these things. You could say the separation energy for a neutron by itself and a proton by itself are both 0. So the total energy on this side of the equation, on this side of the reaction, is larger than the total energy on that side of the reaction. That means that the reaction will happen. And that the reaction will go in this direction. Now, we can also calculate the difference. If we take the difference in energy from the neutron before and of the rest energy of all the particles that come out after, we find that the difference, in the text it's written as delta E, is 0.123 picojoules. That's just the difference between that and that. What does that mean? Well, that 0.123 picojoules, that means that there was more energy at the start than there was at the end. Now we know that energy cannot be destroyed, so that means this must be carried off by another carrier. In the case of a proton, the neutron, the electron, and the antineutrino, it is kinetic energy. So the result of this reaction is that you get 0.123 picojoules of kinetic energy. And that means that the neutron, which breaks apart, turns into a proton, which is drifting away in one direction, an electron, which is whizzing away very fast in another direction, and an antineutrino, which is whizzing away at nearly the speed of light. So the motion of all of those particles whizzing away is what you call kinetic energy, and so the carrier for carrying those away is momentum. So the result of this thing is that you take some energy which was stored inside the neutron and it gets converted into kinetic energy. And when these things collide with the rest of the material around them, they will heat it up, and then you'll have entropy produced.